Hi. This was going to be a short and sweet video explaining how my Etch-A-Sketch circuit works in greater detail, and while I'll do that, it ended up taking me a bit longer than I expected to put together. If you're one of the many people who wanted a closer look at the implementation details, then this is for you. And if you haven't actually seen my previous video about this project yet, you might want to check that out first. But in summary, I built an electronic Etch-A-Sketch from a handful of old TTL digital logic chips. There's no microcontroller here, and most of the parts were manufactured in the 1980s. Not all of the parts are old though. I used some Rotary encoder debouncing chips that were released earlier this year, and these LED matrix panels are definitely modern. So anyway, a lot of you asked for more detail about how the Etch-A-Sketch actually works, so I'm going to try to walk through it. Keep in mind I'm not an electronics expert. I've got no training or professional experience with any of this stuff, and I only started dabbling with these old chips about 6 months ago. Okay, to make this easier to talk about, I spent a lot of time learning how to use KiCad so I could create a schematic as a reference. And KiCad is a free and open source tool for designing schematics and printed circuit boards. It's powerful, but not the most user-friendly software I've ever used, but I got the hang of it well enough to translate my circuit from the breadboard to a schematic. Okay, since the screen is kind of the main interface to the Etch-A-Sketch, I think we'll start there. But before I get into how it's wired up, I wanted to mention that I didn't immediately set out with the idea to make an Etch-A-Sketch. Instead, I was thinking about ways to use the LED modules that I had found to do something interesting, but without using a microcontroller. And the key realization I had was that maybe I could make a screen of LEDs look like it was displaying a solid image if I stepped through each of them quickly enough. I reasoned that a circuit built around such a screen might only need to concern itself with a single LED at a time, and that made the idea of an Etch-A-Sketch a lot less daunting when it finally did occur to me. The fact that it looks like there are multiple LEDs lit, displaying a solid image, is really just an illusion. In reality, it's sweeping through all of the LEDs hundreds of times per second and only lighting each individual one very briefly, according to some simple rules. Our eyes and brains do the work of blending it together, so it looks mostly like a solid image. I wanted a decent-sized screen for this project, but not something too daunting to work with, so I used 4 LED matrix components. Each of them is an 8x8 grid, and they're built in such a way that you can only energize whole rows or columns. The LEDs where the energized columns and rows meet are the ones that can actually light up. I wired 4 of them together by connecting their rows and columns to each other, essentially making one big 16x16 LED matrix. Unfortunately, these models have a very confusing pin layout, which kind of made them hard to work with. I tried to deal with that on the schematic as best I could without having a bunch of wire lines all over the place by using labels. In KiCad, a label represents a sort of virtual wire, so imagine that every label with the same name has a wired connection between them. Using the Highlight Nets tool, it's easy to see where the matching labels are to show what's connected to where. As you can see, I labeled all of the rows of the displays with R_1, 2, 3, and so on, and then I did the same for the columns, like column 01, 02, 03, and they connect into the rows and columns of the actual display units. All 16 columns of my 16x16 display are connected to the outputs of this demultiplexer chip on the left here. And a demultiplexer can select one output at a time. In this case, the chip has 16 outputs, one for each of the columns on my screen. Since digital logic signals are binary and can only be high or low, there needs to be 4 pins of available information to encode all 16 possible output options. These 4 input signals, labeled H0, H1, H2, H3, make up a 4-bit horizontal address that then activates a single column. When all 4 bits are logically low, or 0 in binary, the demultiplexer will select the first output pin 0, which I have connected to the first column on my display. If the input bits were 0, 0, 0, 1 in binary, then the second column would be selected, and so on. For the other dimension of the screen, I use the same setup. So the demultiplexer on the right connects to all 16 rows and selects one at a time using the vertical address bits V0, V1, V2, and V3. So the demultiplexers I ended up using here are actually analog demultiplexers, so unlike digital ones, which would set the outputs to either high or low, These actually act more like electrical switches that pass a signal through them or not. So let's say that row 6 is selected. That should be binary input 0101. Any voltage or signal that's connected to this common pin is passed through the chip to the selected pin. The other pins are actually disconnected, and that's not the same as low or high. They're in what's called a high impedance state, so they're effectively disconnected from the rest of the circuit. Since this is an analog demultiplexer, the common signal doesn't actually have to be digital. It could be anything, technically. It could be like an audio signal or something else entirely. But I don't actually need a fancy signal here. I just need 5 volts on one side and ground on the other side, so there's a completed circuit through a specific row and column of the display. So now, by stepping through all of the horizontal and vertical addresses, every single LED can be lit one at a time. Unfortunately, there is a slight flaw with this that I didn't realize when I designed it, but these analog demultiplexers have a large amount of internal resistance. So while it technically works, the LEDs ended up being pretty dim. I've been experimenting with some ideas to fix the brightness problem, and maybe if they work out, I'll talk about them in a later video, but in the meantime, I'm just working around it by shutting the lights off. Okay, so that's half the story of how the screen works. The other half of the story is spinning through all the pixels really quickly. To do that, I hooked up a 555 timer to act as my clock source. And right now I have it configured for about 48 kilohertz. That means I'm generating a clock pulse around 48,000 times per second. The 555 generates a clock pulse that ultimately drives the whole rest of the circuit, but it's actually only connected in one place. And that's over here in what I'm calling the display address generator. And as you might guess from the name, it generates the display address. The display address is the current horizontal and vertical position of the screen, and it changes hundreds of times per second as we sweep through the LEDs. So these two chips are both 4-bit counters, and that means that they can each count from 0 to 15, or 0000 to 1111 in binary. Each time the up pin on these chips is pulsed, 1 is added to the counter's value until it reaches its maximum value of 15, and then on the next pulse it rolls back to 0 and starts the process over. These two chips are also capable of counting backwards, but I didn't need to do that functionality here, so the down pin is tied high and never pulsed, which disables that. The left counter's 4-bit output is here, and it generates the horizontal screen address that I mentioned before. That's H0, H1, H2, and H3. And they go to the horizontal demultiplexer, which you can see here. They're the same connection. When the counter rolls over from 15 to 0, the chip also generates a signal, and that signal is connected to this wire here, which connects to the second counter's up input. So that means that every time the horizontal counter loops, the next counter chip is incremented by 1. And as you probably guessed, the second counter chip is generating the vertical 4-bit address lines of V0, V1, V2, and V3, which go to the vertical demultiplexer inputs up here. So every time the clock pulses, the horizontal position goes up by 1, and eventually it reaches 15, and it rolls back over to 0, which causes the vertical position to tick up by 1. And then this whole process goes round and round forever for as long as the clock is pulsing. And when tied together like this, the combined outputs of the two counters could be thought of as a single 8-bit number. And the maximum value 8 binary bits can encode is 256, which just so happens to be the same number of LEDs in the 16 by 16 LED matrix. Since the clock is pulsing around 48,000 times per second, and there are previously mentioned 256 LEDs, each individual LED is lit about 187 times per second, assuming I've done the math correctly. Alright, so that's the way the circuit cycles through each pixel, but there's still something missing. In order to show the lines that the user is drawing, we can't just light up every LED on the screen all the time, right? So we need a way to selectively turn the pixels off. But before I get into that, I need to talk about where the pixel image data is coming from in the first place. To store the image, I'm using an old RAM chip from the 80s, and it can only hold 256 4-bit words. And surprisingly, that's actually overkill for this circuit. All I really need is 256 individual bits. But I didn't have a RAM chip like that, so I'll just ignore the extra 3 bits. Since this RAM chip can hold 256 values, it needs an 8-bit input address. And I just so happen to have an 8-bit address if I combine the two 4-bit display addresses I talked about before. As the display address generator steps through all of the addresses, the RAM chip will also be moving through its own data slots one by one in lockstep. Since the RAM chip can store 4 bits per memory slot, it has 4 input-output pins, but the only one I'm actually using for anything is D0. As you can see, D0 is connected to 2 places. One is over here in this buffer, which I'll talk about a bit later, and then the other is connected to this OR gate. And I want to follow this path because the output of the OR gate is the source of the display signal, which controls whether an LED is on or off. For now, we're just going to ignore the blink signal and assume that it's always low. So if the blink signal is low, then the OR gate's output is just going to be the same as whatever D0's input is because it's an OR gate. So that means that when D0 is high, then the display is high, and when D0 is low, the display is low. If we follow where the display signal goes, it goes to these 2 inputs on the demultiplexers. These are enable pins and are named with the letter E here. They have a line over the E, which is an electronics naming convention that stands for active low signal. That means that the logic is sort of reversed here. To enable the demultiplexer, the pins actually have to be low. It's a bit counterintuitive to think about these logic reversals sometimes, and I find myself getting confused by it all the time. Some of the datasheets I've seen flip the terminology around and call inputs like this an inhibit pin instead, because then the high signal inhibits the chip's function. Personally, I think I kind of like thinking about it that way sometimes. So this display signal, which remember is just the output of the RAM's first data bit, because we're ignoring blink right now, is going to these active low enable pins. That means that when the data bit is high, it's actually inhibiting the demultiplexers. And when they are inhibited like this or not enabled, their outputs are all turned off. So to recap a bit, the clock is stepping one by one through both the RAM and each LED of the screen in parallel. The RAM location for each screen location has a single bit that indicates if the LED at the current screen location should be on or off. That bit is routed through these enable pins in such a way that when the bit in RAM is high, the demultiplexers are inhibited and therefore no LED is lit. And if the bit is low, the demultiplexers are not inhibited and therefore they're enabled, and so one LED is lit. This all means that the image that is stored in RAM is actually inverted from how you might normally think about it. The zeros are where the pixel is turned on, and the ones are where it's turned off. And that might be a bit counterintuitive, but that's just how it happened to work out when I was building this. Whew, okay. I was originally hoping that this would actually be a short video, but now I'm not actually sure that's going to be the case. I haven't even talked about input yet. If you need a quick break, now would be a great time to like and subscribe. Okay, so on to the input. The actual physical knob itself is a part called the Rotary encoder, and it has 2 outputs, A and B, and then a third pin, C, which in this case is tied to ground. As you turn the knob, A and B are connected and then disconnected from C. And you can tell which direction the knob is rotating by tracking if A or B triggers first. Rather than building all of that detection circuitry myself, I use this neat Logiswitch chip, which figures this out and creates a nice clean digital output for me. The P output of the chip is the pulse, and it's triggered whenever you turn the knob one click. And in this case, I'm calling it the horizontal pulse signal. And the D output here is the direction, and that is the horizontal direction signal in this case. The vertical control knob is set up the same way, of course, but it generates the vertical signal instead and the vertical direction signal. All of these signals from the knobs go to a new area of the circuit called the cursor address generator. And as you might have guessed, it generates the cursor's address. And just like the display address generator, there are 2 4-bit counters here, but they're slightly different. Each of these counter chips is kept independent for one thing, so there's no rollover between them. Another major difference of these chips is that they can count up or down depending on if another input pin here is high or low, rather than having the separate up and down pins that the display address generator chips happen to have. The combined 8-bit output of these counters are what I'm calling the cursor address. The left chip, which is controlled by the left knob and the horizontal input, generates the first bits, which are X0, 1, 2, and 3. And the right chip, which is controlled by the right knob and is the vertical input, generates Y0, 1, 2, and 3. These addresses determine where the cursor is on the screen, and I'll talk more about how they're used in a bit. Getting back to the input signals, you can see that the horizontal and vertical directions are tied to each counter's DU pin, which is the up-down input. And the rotary encoder chips actually hold their direction outputs either high or low, depending on if the knob was last turned clockwise or counterclockwise. So that's how these chips know how to count up or down. The horizontal and vertical pulse signals from the inputs are connected directly to each counter's clock pulse inputs. So whenever the knobs are being actively turned, pulses are generated, which in turn pulses the counters so they do their things. When the pulses stop coming because the knobs aren't being turned, they hold their current values on their output pins, so the X and Y cursor outputs are always available for other parts of the circuit. Oh, and you might have noticed that the pulse signals here have a line over them. If we follow that, you can see that I have two inverters that are actually flipping the original pulses. I needed to do that because the counters update their clock pulse transitions from low to high, but the direction signal wasn't always updated by the time the counter chip needed it to read it to decide if it should count up or down. And that caused input lag when changing directions. So inverting the pulse fixed it by shifting the signals slightly out of phase. Okay, so we have the two main pieces, input and output, and now they just need to be tied together. Somehow we need to set a bit in memory to 0 wherever the cursor is. Since the clock is spinning through every LED and RAM slot really quickly, I decided the easiest thing to do was continuously check if the current screen position matches the current cursor position, and use that as the signal to write 0 to the RAM or not. So the first step is figuring out where the two addresses match. To do that, I used an 8-bit comparator chip, and this chip tells you whether two different 8-bit values are the same or not. It can also tell you if one is bigger than the other, but I didn't need that functionality for this circuit. One of the inputs to the comparator is an 8-bit number made of the two 4-bit screen addresses, and the other input is an 8-bit number made of the cursor's two 4-bit X and Y addresses. Whenever the two outputs are the same, this pin here goes low because it's an active low output. That signal is routed over here to an AND gate, and like before, I'm going to ignore the other signal here for the moment and follow the output, which is the read-write signal. If you'll note the line above the W, this signal means write when it's low and read when it's high. And that makes sense because the comparator's output is also inverted. It's low when the screen and cursor addresses match, and that's exactly when we want to write to RAM. The read-write signal goes to two places, to this buffer and then to the RAM chip itself. And I glossed over this buffer before, but now we need to talk a little bit about it. The RAM chip has 4 data pins, as we saw before, but sometimes the pins are output pins, like when reading the data, and sometimes the pins are input pins, like when we want to store something in the RAM. So we have to be careful about sending signals into the pins that are set to an output mode. That's sometimes called a bus conflict, and not only does it mess up the signals so that they aren't electrically clean high or low values, it can even cause damage if things go especially badly. So we want to avoid that. That's the job of this buffer here. Now this particular chip is overkill for what I needed here. It actually has two separate 4-bit channels on it, A and B. I didn't need channel B at all, and so you can see that all of those outputs are marked unconnected, and the inputs are all tied high because I'm not using them. Also remember that we only really need a single bit of input for our RAM, so we don't need the other 3 lines of channel A either, which is why they're all tied to high here. On the schematic, I wired up all 4 I/O lines from the RAM to the buffer's output, but only D0 matters. On the input side, only channel A's input bit 0 has a signal actually hooked up to it, which I labeled the bit signal here, and we'll see where that comes from in a minute. Alright, so that was a long-winded way of explaining that I'm essentially using this entire chip to enable or disable a single bit. It occurs to me now that I might have been able to replace this whole entire thing with a single transistor, but anyway, moving on. So when the read-write signal is low, it means that we want to be in write mode, because the display and cursor addresses are the same. And when they are the same, we want to enable the buffer's output so that it connects this bit signal that we're trying to write into the RAM's D0 line. There's a lot of inverted logic happening here. It can be confusing to follow. So the important thing about this particular chip is that when it's disabled, the outputs are all disconnected. They're in the high impedance state, just like how the demultiplexer outputs are disabled when unselected or inhibited. This prevents sending any signals into the RAM's data bus lines when the RAM is in read mode and its data lines are set to output mode. However, when the screen and cursor addresses match, the RAM chip is switched to write mode, and the buffer's output gets enabled at the same time. So that means that this bit is routed through the buffer to D0, which is allowed to then go into the RAM chip. Okay, that was probably confusing, but I'm really not sure how else to explain it. Feel free to pause and give it all the good think if you need to. I'll be here waiting. Okay, back? Good. So, what is this bit signal that's being written anyway? When drawing, we always want the bit signal to be low, because if you remember, and I forgive you if you don't, the image that's stored in the RAM is actually inverted. So we need to write zeros wherever the cursor is at to make an LED turn on. The bit signal could just be tied directly to low here, and actually I did that when I was first developing the circuit. But it was almost immediately obvious that I needed a way to clear the screen of the Etch-A-Sketch II, so I came up with a simple way to do that, by changing the value of the bit signal. If we track back to where the bit signal actually comes from, it comes from this inverter, which is inverting another inverted signal called clear, which comes from the right input knob's rotary encoder chip. I didn't mention this before, but these rotary encoders can be pressed down, which activates a switch inside of them. The rotary encoder chips support this and have a connection for it, so the right knob's push button is wired through the chip and comes out here as an inverted clear signal. And I marked it inverted because it's normally high, but when pushing the button, it changes to low. So whenever the right knob is pressed, the clear signal is pulled low, and by following the connections back to where we started, it means that the bit signal goes high. The inverted clear signal from the knob is also going to this AND gate that I glossed over before. So now you can see that when the button is held down, this signal is low, which means the AND gate output will always be low. So that means that pressing the button down forces read-write mode to be in write mode because write is the low signal. Since the clock is spinning through the RAM really quickly, holding down the clear button for even the briefest moment ends up filling the RAM with ones, which makes the screen go blank. It was difficult to see where the cursor was when you started drawing, so to fix that I added another chip which counts whenever the cursor signal is triggered. Recall that this signal is only true when the display and cursor addresses match, so it only happens once per screen refresh. This chip is set up so that it essentially divides by 16, so every 16 updates of the screen, the last output bit is toggled between high or low, and that generates this blink clock signal, which is ANDed with the cursor, which creates the blink clock signal, which in turn is ORed with the RAM's current data bit. So in this way, the display signal pulses on and off, but only at the cursor's location, which creates a blinking effect. And with that, I think I talked about every single part of this circuit. All taken together, it makes for a pretty neat little toy that was a lot of fun to design and build, and is very satisfying to play with. Well, if you made it this far without falling asleep, I appreciate it, and with any luck, maybe now you have a better idea of how the whole thing works. And as always, thanks for watching, and I hope you'll stop in again next time. Bye.